Okay, so now we are going to see two very fundamental things about spin. One is how we actually measure spin in the lab. And the second is something very fundamental about the Bloch sphere representation, which may have seemed like just a mathematical construct. But actually, it turns out there's a very important physical meaning to it. And it provides a way of actually manipulating spin in the lab. Okay, so let's start. Let's first start by seeing how we actually measure spin in the lab. So the idea is to use the fact that the spin of an electron creates a magnetic moment, which allows us to grab hold of the spin in the lab and thereby measure it. Okay, so the way we are going to grab the spin, this magnetic moment, is through an external magnetic field. But the kind of magnetic field we'll create is sort of a funny field. It's going to be a non-homogeneous field. And so here's what the apparatus is going to look like. So we'll take this kind of a funny looking tip together with a more straightforward looking bar magnet, so that the magnetic field actually looks like that, where it's very strong here and then it becomes weaker as we go up. And now imagine that we have an electron that we are allowing to pass through here. Now, if you look at the path of this electron, it turns out that depending upon the state of the spin state of this electron, this path either bends up or it bends down. Okay? And if you analyze it further, it turns out that if the state of this electron that you input was psi, then if psi was spin up, if the spin was pointing up, then it takes this upper path. And if it was spin down, then it takes this lower path. So this was also what we might call 0 and 1. And so if psi happened to be in the state alpha 0 plus beta 1, then what this apparatus does is it neatly separates out these two cases. Right? So if you were to now look to see where the electron is, okay, so if we looked here and figured out where the electron is sitting, which path it's taking, then we'll see this with probability alpha squared and that with probability beta squared. So this is a way of measuring the spin state of the electron. Now this is an experiment that was first done in 1922 by Stern and GERLACH. And what they actually did it with was not electrons, but they did it with silver atoms. So now, why does this work? So to see this, let's give a semi-classical explanation. So when you have an external magnetic field, so-called B field, the spin interacts with this external magnetic field because the spin itself, the electron itself, is like a little magnet. And in fact, the energy of this electron, if you had a little magnet with magnetization mu, then this would be the energy of that magnet, depending upon which direction it's pointing. So if you consider the fact that the magnetic moment of the electron points in the opposite direction from the spin, then it turns out that the way that our spin wants to orient itself is that the spin down state, the energy is negative, and the spin up state, it's positive. Right? So the spin wants to orient itself opposite to the external magnetic field because that's a low energy state and it's a favored state. Okay, so now what happens if we take the electron and pass it through this non-homogeneous magnetic field. So, well, if it's in a spin down state, then it's energetically favorable. It's in a low energy state, and in fact, because this field gets stronger as we go further down, this spin wants to be as far down as possible. So it actually feels a force that's pushing it downwards, and that's what bends the trajectory downwards. Whereas the spin that's pointing up, well, it has a positive energy, and so it has a force that's trying to move it upwards, where the positive energy becomes as low as possible, and so its trajectory actually bends upwards. And that's sort of a semi-classical explanation of how this Stern-Gerlach device works. Okay, so now let's do another sort of experiment where we take this Stern-Gerlach device and we now point it in a different direction. And if we were to take this electron and if we were to push it through here, what do you expect would happen? So would you now see something very different, or would you still see the electron bend either up or down? And what would make it bend up or down? So the answer to this really lies in understanding the Bloch sphere. So let's go back and look at the Bloch sphere. So let's say that okay. So the answer to this depends upon the Bloch sphere. So let's say that the direction in which this was pointing is the direction u. So this was pointing in the direction z, right, along the vertical axis, and here we are pointing the Stern-Gerlach device in some arbitrary direction u. So the first thing we do is we locate u on the Bloch sphere. So u is pointing in some direction in three-dimensional real space, and it's specified by angles theta and phi, and it corresponds to a quantum state phi sub u, which is cosine theta over 2, 0 plus e to the I phi sine theta over 2, 1. That's what the Bloch sphere tells us. So it turns out that if we were to point our Stern-Gerlach device in this direction u, and if we take an electron and we pass it through here, then it does actually take one of two paths, where the upper path is taken if the electron were in the state psi sub u. And what about the lower path? Well, if you look at the antipodal point, if you take the opposite vector minus u, and now look at the state psi sub minus u, that's what comes out this way. And what's psi sub minus u? Well, it's an exercise, but you should be able to figure out that it's actually sine theta over 2, 0, minus e to the I phi cosine theta over 2, 1. Okay, see if you can work this out. Okay, so of course these are two orthogonal states of the spin qubit, and so if our original state psi of this electron was alpha psi sub u plus beta psi sub minus u, then if you measured which direction the electron went after going through the Stern-Gerlach device, then you would see it here with probability alpha squared and here with probability beta squared. Okay, now it turns out that, if you were to take two such Stern-Gerlach devices, one of which was pointing in this direction u, as we said, the other pointing in some other direction, let's call this direction v, and suppose we allow our electron to go through the first one. Let's say it bends upwards, and then and then we sort of take it and pass it through the second device, and we want to know what's the probability that we'll see it bend upwards here too. Okay, so experimentally it turns out that the answer to this question is very simple. The answer is the probability that, given that it bent upwards here, that it actually also bent upwards there, is 1 plus the inner product of u and v. So if you look at v and u, if you look at the angle mu between them, this is like 1 plus cosine mu over 2. And if you remember your trigonometry, this is exactly cosine squared mu by 2. So this is an experimental fact. And now if you instead look at what's happening behind the scenes with the quantum state, the state in the two-dimensional complex vector space, right? Then the fact that this bent upwards here means that we were at this point, the state of the spin was psi sub u. And then we are asking, what's the chance that when we measure it, it'll make a transition to psi sub v? And the answer is, so in other words, we start with the spin in the state psi sub u. It happens to be in the state psi sub u. And we are now measuring it in the bases psi sub v, psi sub minus v. What's the answer? What's the probability we see this outcome? Well, it's whatever this angle happened to be. Let's call it nu. So it would be cosine squared nu. Okay. But now, what's this angle nu? Well, if you work it out, if you look on the block sphere and if you see what the angle between these two vectors would be, it's this factor of 2 that creeps in. And you see that nu is exactly mu over 2. And so the answer is exactly consistent with the experimental results. So, in other words, what this is telling us is that there's a physical significance to the block sphere. That you can really, even though spin lives in this two-dimensional complex vector space, we can really think of it as living on the block sphere. And then whichever direction the spin is pointing in the block sphere, that's sort of the direction of the, that's sort of how the magnet is oriented. And that's how the spin is going to interact with the external world.